Today we will start a new series about the basic elements in the deep learning framework. First of all, we will discuss two most basic tasks in the deep learning program: the regression and the classification. And we will discuss the output vector for both tasks and the loss function associated with them. For regression problem, the input of a deep learning problem, the program could be a number or a vector or a tensor, which is a multi-dimensional array. And we can have a lot of different input data here. And those data will be sent into a function. Those functions, we can send it as a breadbox. And it could be a mathematical function, or it could be a neural network, or it could be any functions here. And those functions will output a single number for a regression problem. So the single number could be, for example, the number could be a price for the stock in a stock market prediction problem, or it could be a death rate for disease prediction models. And for this kind of the problems, there is a special form of regression which is called linear regressions. The linear regression is the most simple model, and it will using a linear model or linear function to make the prediction. For example, in here, in a house price prediction model, we were using the area of the house and the age of the house to predict the price of the house. Okay, so we can collect a lot of the sample from the historical data to get the pair of data between the area of the house, age of the house, and the price of a house. So we can collect a lot of the data here. And then we will try to build a model to make a prediction by using the area of house and the age of the house to predict the price. So that if when we see a new house, so that the only thing we know is the area of the house and the age of the house, and we can using this data to to predict the price of the house. So in this way we can learn from the historical data to predict the price of the house by using the property of the house, such as the area and the age here. And for this formula, the generic form is like this one. So we will have a lot of the input data, which is the S1 to the SD. And for each of the input parameters, we can have a weight for them, so which is the W1 to the WD here. And then actually we can write this formula as a matrix form by writing it as a W transpose dot X plus B. So this will become the Y. So in this case, the X will be a two-dimensional vector, who each of X will be an area where two elements, which is the area of the house and the age of the house. And then we can using the area of house and the age of the house to make the prediction. And if we have a multiple XY pair here, we can actually write the above formula as this form. You will become a capital X multiplied W plus B. And actually we can explain this formula by this way. So the capital X is actually composed of a number of the X, which is the one sample here, one input data here. For each row, it will be a sample in the data set. And then when we do the matrix multiplication, we will actually using a row to get the inner product between a row and a column W here. So that for each of this, we will produce a prediction. So actually in this form, we can using a simple matrix multiplication to make a prediction for a lot of samples. So the question is that we need to, if we have a lot of historical data, which has the area of house and the area of house and the price of house, so we need to decide the best W and the B here, so that we can just use this formula to make a prediction of the price of the house for new data. So for example, if we found a new house in this area, so that we can using the size of the house and the edge of the house to predict the price of the house, even though we don't know the price of the house yet, because the house has not been sold yet. But the problem is that how do we decide what's the best W and the B for the model? The question is that we have a data set. This data set is history of the historical data of the house market. So we have the area and the edge of the house, and we have a price of the house here. So from those historical data, we want to decide the best model, which can using the edge and the size of the house to predict the price of the house. And so that we only need to know the size, the area, and the edge of the house, and so that we can put into this formula to get the prediction. And we hope that the y1, y2 here should be as close to the y1, y2 here as possible. So we hope that this will be close to this one. And in the linear algebra course, this is called a data fitting problem. So that if we have only two sets of data here, and since we have the two variables W and B, and we have two sets of data, so that we can simply solve the linear equation to get what the W and the B should be. But if we have more than two sets of samples, for example here, we have n samples. In this case, it's impossible for us to find a set of WB which can satisfy all the samples. because we have more equations than the variables. And in the linear algebra problem, this will call a data fitting problem. So that instead of write a set of WD which can generate a precise value of the y here, we try to get a set of W and B which can minimize the error of a prediction. So it means that we will try to get the value, a set of WB, which can generate a set of the y hat here, and the difference between the y hat and the y will be the minimum value. So in the linear algebra, that's called data fitting problems. But in the other hand, we can look at the same problem by using a statistical way to do the job. And for a statistical way, we will assume that there is some error in the y here. So it means that the y1, y2, and the y1 will be a little bit different from the value predicted by the model. And the x1 here is the error term. And the x1 should follow some distributions. And typically, we will assume that it will be the normal distribution. We will discuss it later. But since this is a random error terms, so we can try to do a job. So instead of define a formula, we define a distribution instead. So it means that the value instead of using a formula to predict the price, and we using a normal distribution here, and whose parameter is the mu and the sigma. And then we will, for a specific x here, we will try to decide the mean value by using this formula, and then we sample data from the distribution to be the y here. So in this way, we can try to generate a data set. For example, we can just sample the value. We know the x1, x2, and the xn, so that we can substitute the x into this formula, and do a sampling to get the y hat. And we hope that we will try to find a set of the WB which is maximize the probability or the likelihood we will generate this particular data set from this formula. This procedure is called maximum likelihood. And before we discuss how we can calculate the maximum likelihood, we will try to define what is the normal distribution here. So in the normal distribution, it means that you will follow this formula, and the distribution will be decided by two parameters, the mu and the sigma. Okay, so the curve, typically the curve will look like this picture. Okay, and actually the normal distribution is very important distribution because of the central limit theorem. So in this theorem, it tells us that if we repeat the random process for many times, the result will cause to a normal distribution, no matter what the probability density function is. So for example, if we flip a coin for many times, the probabilities of the of the each size is 0.5. And if we fit it for example, for 10 times, the mean value should be 5 here. But actually, so if we fit it for 10 times, we may think that because of the probability is 0.5, so we should get the 5 up and the 5 down. But actually, if we fit for 10 times, we might have some probability to get the 4 up, 6 down, or 4 down, 6 down as well. Or even the 1 up, 9 down, or 9 up, 1 down. We still, overall, the probability is much lower, but we still have some probability to get this kind of result. So, but the central limit theorem tells us that the distribution, the probability of all those situations will follow the normal distribution here. And the distribution can be decided by 2 parameters, which is the mean value. So what's the value with the maximum probability here, and the deviation, which decided how wide the distribution is. It may be like this way, or it might be wider. So it means that the mean value is the same, the deviation is different. Okay, so after we know the normal distributions, so we can try to decide what's the likelihood to see a particular y for a given x. So it means that what's the probability to get the particular data set in a random process. So for example, if a random process is decided by this formula, okay, so actually this formula can write in this way. So it means that the y is the tier here means that the y is sampling from a normal distribution whose parameter is mu and sigma, and the mu is decided by this formula. So in this formula, we have two parameters, w and b here. So for each of the x, we can decide a mean value, and for a specific sigma, which is a deviation, we can define a normal distribution, and then the y is actually a sample from this distribution. So from the definition of normal distribution, we can know that the linear function decided the maximum probability for the result, but we still have some probability to get the value slightly different from the mean value. And the actual formula is the normal distribution here. So for each of the x, we will decide a distribution, and then we can know that for a specific x, and if we can get the probability of the specific y here. So that this is for the one sample. So it means that for a given x, what's the probability to get a particular y? So for example, if we know the area, the size of the house and the edge of the house, and we know the distribution of the price of the house by using the normal distribution. And the only thing we need to decide is just the w and the b here. And those two numbers can be decided can be decided by the historical data. So the question is that how could we find a set of w and b which can maximize the probability to get the data set? So for a specific x, we can use this to get the probability of the y. And if we we repeat the same process for each sample, so it means that we can get a set of the x. And it will produce a set of the y here. So it means that this will be the probability of the entire data set. Okay, well, what exactly this value is? Actually, for each sample, the probability is this one. So if we have n samples, make n samples, so the probability of a total data set is actually the product of all the probability for each samples. And then we can just put those substitute the p of the xi yi by using this formula, and it will actually, since the product of the exponential will become the sum of its exponents here, so this function will become this one. And in order to get a maximum value of the entire data set, we actually need to minimize this summation here because there's a minus sign here. So we need to minimize this term. Okay, so if we can find a set of the W and the B which minimize this term, it will give us the highest probability to see the data set. So that's the W and the B we want here. And actually this term is actually the mean square error of the data set between the prediction of the model, which is the W transpose X plus B here, and the label data. So this actually is the error of one sample, and we square it and make a summation to get the mean square error. And this is actually the error we are using, but that in the data fitting problem in the linear algebra. So actually, both of the methods will get the same answer. So this is why we always need to using the mean square loss in the regression problems. So minimize the mean square error is equivalent to the maximum likelihood estimation of the linear model under the assumption of the additive Gaussian noise. The additive Gaussian noise is actually this term here, the exon here. Okay, so now we know that why we need to using the mean square error for the regression problem. And the second kind of task in deep learning is the classification problem. In the classification problem, we will decide the probability for each class for a specific input data. For example, if we have an image, and we send the image into a function which is the model, and we will make a prediction to say that if this image contains a dog, a cat, or bird, or a pig. The first question is that how could we represent the dog, cat, the bird, pig here? A simple answer is that we can use a number for that. For example, the 0 is dog, 1 is cat, 2 is bird, 3 is pig. But the problem of this approach is that there is some assumption between those categories, because 0 is close to 1 and far away from the 3. So it means that the dog is more similar to cat than to the pig. Of course, for the dog cat case, it looks like uh, 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 a good assumption. But actually, for a classification problem, it's not always this case. We don't like to have such kind of assumption between the categories because that may not be true. So instead, we are using a vector for each class, and the most simple way is using the one hot encoding. For example, for a dog, we're using the 1000, and the cat, we're using the 10100. For the bird, we're using 0010, and for a pig, we're using a 0001. So if we have a forecast, we're using a 4-dimensional vector. And if we have a 100 different class, we are using a 100-dimensional vector. So it looks like this is very inefficient, but actually, this is the best way to do the job in order to prevent there's any assumption between the categories. And actually, that's why it's used in all deep learning network today. But problem is that we can see that in the one hot encoding, the output of the model should be to be 1 0 0 0 like this one. And actually, this looks like we can, although it's not necessary, but we can think this as a probability distribution. For example, for the dog, it means that the first element is the probability of the dog, and the second element is the probability of the cat, and the third one is the probability of bird, and the fourth one is the probability of the pig. So that it means that the output vector must be a probability distribution. But in order to be a probability distribution, the summation of the output layer for the O1, O2, O3 must be 1. But in a neural network, it's hard to guarantee that. And if we hope that the model will do the job for us, it's not easy for the model to make the 3 value, the summation of 3 value to be 1. Typically, we will add a softmax layer after the output layer and force the output value to be a probability distribution. It means that the summation of all the value to be 1. So the formula of the softmax is like this one. So in the denominator, we just we sum all the values in the denominator, and in the numerator, it will be one of the items here. So if we would take a summation of all the I here, and so it means we just the summation here, the numerator and the denominator will be the same, and this will be the 1. So it will be a probability distribution. So the main reason we're using the softmax to convert the output into a prediction is that it will guarantee that the Y will be some kind of a probability distribution here. So it will be easier for us to interpret the result. But we must be very careful that this probability distribution is not a real probability. in more we may we may think that this is, for example, if one value is 0.6, the other value is 0.3, it doesn't mean that the probability is double. It just means that the 0.3 is more likely to be less accurate than the 0.6. It means that a probability of 0.6 is more possible to be, in this case, compared to the value of 0.3. But it doesn't mean that the probability is double, because this is not real probability here. So we must be very careful to interpret the result. So for example, if we have a probability value which is 0.9, the other one is 0.7, the probability might be very close or might be very far away. We should be very careful to think it as an absolute value of the probability. Okay, so for the softmax function for the classification problems, it need a loss function as well, which we will be using to compare the prediction to the ground truth. And typically, we are using the cross entropy here as the comparison functions. And I will not discuss the reason in detail here, but if you are interested, you can check the link here to see the more detail, because this is part of the discussion called generalized linear model, and from this series we can know that the cross entropy will be the best loss function for the classification problem when we're using a softmax here to generate the output. But this mathematics is quite complex. So if you don't want to go into the detail of the math, you can just treat this as a truth. So when you doing the classification problems, you always using the cross entropy as a loss function. Because now in the future we will learn more loss functions, and those functions will be very complex, and we will add some regression turn into it to make it very difficult to analyze those functions mathematically, so that it doesn't matter if you are not understand the math for the reason why we want to use in the cross entropy as in the classification problem. You just remember that, okay, that this is the way we should go for the classification problem. That's good enough. Okay, so in the next video we'll try to discuss how to train a neural network.